In the case of single slit diffraction, we know that this is a small slit of width, say it is A, and if we put a screen over here, okay, then we'll see a pattern of fringes. So for example, we'll see as here, this bigger one is the central bright, okay. This one is the first dark. This one is the first bright. In this way, we can get the alternate bright, dark, bright, dark in this kind of sequence of the fringes, okay? These are the fringes we'll see on the screen. But from this graph, it is clear that the intensity at each bright spot, or we also call it the fringe, are not same. You can see in the graph, the intensity is highest for the spot where it is the central maximum, okay, and the intensity goes down if we move to the other band, okay. So this is the first bright. So this can be again seen in this simulation, okay. You can see in this simulation that the intensity of each spot is different, okay. So you know that it changes with the slit width, and it also changes with the distance to the screen, okay. The width of this peak also going to change that, okay. So in our case, we'll talk about what is the intensity, okay. So the intensity in single slit is I, we represent by I, where I equals I naught sine beta over beta, this is squared, okay. So in this case, what is I naught? I naught is the intensity at theta is equal to 0, means it happens for central bright, okay. So here we defined the term beta. So where beta is pi times A times sine theta over lambda. So we just defined this variable b, beta. So here A is the slit width, and theta is the angle for the given bright spot or bright fringe, okay, for the given bright fringe. And lambda is the wavelength of the light used, okay. So this equation can be used to find the pattern. What is the intensity pattern at each point, okay. So in this graph is plotted across intensity along axis y and this the variable we defined beta along the axis x. Okay, so we get this kind of pattern. So we are going to simplify further that. Okay, and let's see, we move forward. We know that before a sine theta equals m lambda. We know that this is for m dark fringe. Okay, dark fringe. So let's see, dark fringe or dark spot. So let's put here, if m is equal to 1, we get the first dark. In that situation, we can write a, say for example, then sine theta will be equals to 1 times lambda. Okay, so this means sine theta equals lambda over a. Okay, so let's see how we can write this value of beta in term of this angle. Okay, so we know that we just defined beta equals beta equals pi times a sine theta over lambda. Okay, so for first dark fringe, we can write this value beta will be pi times a over lambda. This sine theta could be replaced by pi over a. So we can write here this is pi over a. So this means if you simplify further, this a cancel out, lambda cancel out. So in this case, beta equals to pi. Okay, so let's go for the other one. So for second dark fringe, we can write here this beta equals pi a times pi a over lambda. We need to replace sine theta. So let's see here, if we have m is equal to 2, we can write this as, from this equation, a sine theta equals 2 times lambda. Then in this case, sine theta equals 2 lambda over a. So if I replace sine theta for the second dark fringe by this, then we get it is 2 lambda over a. Then further simplification gives me beta equals to pi. Okay, so this means if we go similarly for third dark fringe, we have beta equals 3 pi. Okay, that's the reason you will see in the plot, like for the first dark, you have beta equals pi. You see here beta equals pi, the value of beta. For second dark, it is 2 pi. For third dark, it is 3 pi. It is keep going like this, just like this. Okay. So let's see here, and we can write as a form of summary. So we have four dark spots or dark fringes. In fringes, we have intensity 0 is 0, and we just figure out that beta will be either plus and minus pi, plus and minus 2 pi, plus and minus 3 pi. Okay, it will keep going just like that. So we can say the value of beta is just m pi, and this m pairs is plus and minus 1. It could be plus and minus 2. Plus and minus just represents that to the both side of the central bright. Okay, so this is all about for the spot which the we get the intensity is going to be 0. Okay, for the dark range. Let's talk now about for the spot where the range is bright. Okay, so we see here that for the case of for the case of central bright, our value of theta is 0. Okay, because if you remember the previous case, say we have this, each point on the slit behaves as a source, so we will consider all the rays parallel to the this direction. Okay, this is the slit, and this is the screen, and we get here is the central bright. Okay, so in that scenario, let's put this. So the angle theta is 0 with respect to original direction of rays. Okay, so if this theta is equal to 0, we can plug that number in the value of beta. Okay, so let's see, because we know our beta is, if you remember, pi a sine theta over lambda. So in this case, we can write pi a sine, this angle is 0, over lambda. So this gives you value of beta is 0. So we know that from calculus limit beta tends to 0, give you sine beta over beta will be 1. Okay, so this means, since we know that our intensity is I naught sine beta over beta squared, so in this case our I equals I naught for the case of central bright. Okay, so if we move further, we'll find that for first bright, the value of beta is 3 pi over 2. So the question is how we can say 3 pi over 2. It comes from here. If you see the position of dark, plus pi gives the position of first dark, and 2 pi will give the position of second dark. So just you can see here in the screen. If you see the screen, so here your say this is your first dark. For this, the value of beta is pi. Okay, for second dark, we have value of beta is 2 pi. So this one is the central bright, and we know that our first bright will be here. This will be the position of first bright. If this is the position of first bright, the angle must be in between. I mean, at the center, we can take the average value of pi and plus 2 pi. Okay, so this will be just 3 pi over 2. Okay, so if we plug this value, plug it in I equals I naught sine beta over beta squared. This is the intensity in the case of diffraction. It will give you, say, I1 intensity for the first dark will be, sorry, first bright will be roughly 0.045 times I naught. So just only 4%. So you can see here, you see already in the pattern that intensity of first dark is very, very small. Okay. So from this point, you see that intensity will be going down. Similarly, we can find the intensity of the second dark. Okay. So let's find the second intensity of second dark. So for second bright, the value of beta will be 5 pi over 2. By the similar region we talked about before for the first bright. Okay, so we'll find that intensity of second bright will be nearly equal to, we say nearly equal to 0.015 times I naught. Okay, and so in the, so we can find similarly. So in the summary, we can say that beta equals 2m plus and minus 1 over pi over 2. Okay, so m equals plus and minus 1, m equals plus and minus 2, m is equal to plus and minus 3, and keep going like this for the bright spot or for bright fringes. So clearly on those spots, intensity will not be same, but we can say clear that intensity I will not be equal to 0 at each spot. Okay, so it will keep going just like this. So this plot will show you this plot 3 shows the variation in intensity plot with slit width say A. So you can see that if slit widths going bigger and bigger, we get the more sharp peak. So for example, here in this case, the slit width is 5 times of lambda. In this case, the slit width is 10 times of lambda. So in this case, A is equal to lambda. So as the slit width is increasing, means bigger and bigger, we can see from this picture that we can also obtain, we can easy to see the other like first order of like first bright fringe or second bright fringe. We can see that. Okay, we can see this in the case of simulation also. So for example, in this case, say I'm changing the slit width as say in this case, you see my slit width is in this range. You can see here slit width is in the micrometer, it is here. Okay, so you just see the central peak. We can just see in this case, we just see the central bright, okay. If I'm going to change that, what will happen? Let's say I'm increasing that. Now at this position, if I'm going to change the if I'm going to change this to in that number more than the 13 micrometer, in this case I can also see the central bright plus say, and I also see the here say first bright position also, and I can also see the position of first dark. Okay, so the slit width plays a role to see the different order of the diffraction pattern. So if you understand up to this point, you can solve this problem for the practice 2 problem. Okay, so let's move forward with the diffraction. Not only one slit is we are taking the case of 2 slits. Okay, so in this case we are talking about not only just one slit. Now we have slit 1 here, other slit 1 here, so I have 2 slits. Okay, so in this case I have 2 slits. If I have 2 slits, so you know that as before we have because this first slit and this one is the second, this both behaves as a source. So this may be the source S1, this may be the source S2. So if we talk about the previous scenario, we know that there is a interference because we have 2 sources, interference, and we have also at the same time a diffraction from each slit, Okay, so they are going to superimpose. So means now we have the combined effect. They will superimpose. So we have the combined effect. Okay, interference and the we have this diffraction. So one point we have to consider in this scenario is that be careful. The scenario we are talking about, say for example, we can include one the case. We have to consider the scenario. We used a sine theta or d, whatever. A sine theta equals m lambda for m dark fringe in diffraction through each slit. Okay, at the same time we know that a sine theta equals m lambda. This is the case for m bright fringe in interference. So be careful about that. Equation is similar, same equation, but they represent different things. So here A represents the slit width. Okay, so this means at some region the effect of interference will cancel the effect of this diffraction. Okay, so based on that equation we can say that the interference, in the case of interference, we have all intensities equally bright. We see that. Okay, in interference all intensity is equally bright. We can see in the simulation also. So let's see if we have only the case of this interference in the case of interference, all brights are equal in intensity. Okay, you see here. If you consider only the case of say single slit, you have this kind of pattern. Okay, so this will be true in interference, but in the case of diffraction, all brights have different intensities. Okay, we see this thing. Okay, so if we have the case of interference and diffraction due to the two sources, they superimpose. Okay, if they superimpose, then their pattern will be different. Okay, so you will see here that the superimpose, interference, and the diffraction, that's the region that, by the way, here D represents the slit width. In general, I use the A. So A is just a symbol. Okay, we can use A or D, whatever. So based on that, at some point, we see that they cancel the effect of each other. So that's the region that we cannot see the missing order M is equal to 3. So you see this color is for the interference, that color is for the diffraction, and this red one is the total effect. Okay. We can play with some simulation over here. So let's see, I may have someone. So this is the case for just for one slit. This is for one slit. Okay, so this is for one slit, single slit. Okay, this is the center one, right? If I change, say, number of slit to different one, say I change n is equal to 2, you will see the pattern is different. So this pattern is for n is equal to 2. So we have two slits, and in this case we have both interference and the diffraction, and they superimpose each other, and they give you the net effect. Okay, so if we keep moving just like this, if we could keep moving just like this, we'll see that that third order bright is missing at this point. Okay, so let's keep moving. Not just two slits, we could have many slits. If we have many slits, then it is called the diffraction grating. It's called diffraction grating. So it is many slits. Okay, so this like diffraction grating consists of a large number of evenly spaced parallel slits that produce interference pattern similar to, but it is much sharper than the double slit. So this means in this time we have many slits, one, maybe two slits, three slits, maybe hundreds, thousands of slits. So each has each width same A. So this is the slit width for each one, and we have such kind of slit is many slits. So this is called the diffraction grating. Okay, so in the case of diffraction grating, we'll see the bright, center bright, first bright, second bright, third bright, and keep going like this. Okay, so in the case of diffraction grating, depending on the color, which kind of color we are using, if you are using the, if this is the case, if you are using the white light, and this is diffraction grating, then at the center we have band is white. After that, we'll see this colored, maybe this is the first order. We see the first order band in both sides, then we get the second order, and just like this. Okay, so this kind of thing will keep going, and these are the examples of this diffraction. So in the case of diffraction grating, a spacing D. So in this case, instead of A, we are taking the D. Okay, so just like D. If D is the spacing for each of these, then we use D sine theta equals m lambda to find the position of the bride. So m is equal to 1 will give you the position of first bride. Yep. And m is equal to 2 will give you the position of second bride. Okay. So generally 1 over D we call the grating element. Okay. So for example, 1 over D is 10,000 lines per centimeter, means in 1 centimeter we have 10,000 lines, 10,000 this kind of slits. Okay, so based on that, we can use this equation to find the diffraction grating. So in this simulation, I will show you that if we have many slits, say instead of only 2, we have many thousands. Okay, so we can interference pattern will change. Say for example, this one. Okay, so let's see one more here. If we considering about this grating, diffraction grating, we can change. Say for example, in this case, the screen to grating distance is, for example, 6.9 meter, and this is the grating lines per millimeter. I took it 500. I can change this value of lambda. Okay, so we get different order of band. So this one, first bride, second bride. Okay, so I can change that number. I will show you here. If I change the different color, diffraction grating, depending on the, you know that this, if you change the wavelength, the color will also change. So this shows you how we can see the patterns. Okay, we can also change the distance between slit and the grating. It will change. Okay, and this number also affects how we are getting the fringes. So this is the case for that. So if you understand up to this point, you can solve this problem. For this problem is related to diffraction grating, and I believe you will do it.